So hello everyone, let's start Alpenglow consensus protocol line by line proof analysis. So for let's run model checker. It will run till I explain how everything is going on. So let me run first a correct normal model. Okay, so let me show you uh, what are my model checking and okay, so my constants are nodes. So I have taken 4 nodes, n1, n2, n3, n4. Max slots I have taken 4, in which first slot is genesis, and the max slot means the fourth slot. So by the end of the model checker we will get block processed for second slot and third slot, because fourth slot we will skip that slot, the maximum slot will be skipped. We have written the logic in that way. Window size for a leader who is proposing a block is 2. That means for 2 consecutive slots they can propose a block. And gamma and total shreds are 4, and gamma is the required shreds to get original data. These two are the parameters of eraser coding. Block time is 1, network delay is 7, genesis slot is 1, because I said you the first slot will be a genesis slot. Byzantine node, we have taken 0 Byzantine node because this is a correct normal model config. Correct blocks are b1, b2, b3. Malicious block is m1. By the way, this doesn't require a malicious block because the Byzantine node is not present there. If we can empty this, then also it can run. Okay, rotor relay nodes are n1, n2, n3, n4. Okay, these are the rotor relay nodes. Max time is the time maximum time that will take for the total processing of the 4 slots is 15. These are some of our invariants, and this is the node symmetry, because there will be a lot of permutations. So to reduce the permutations in between n1, n2, n3, n4, we have taken a node symmetry. And deadlock is false. Okay, so let's go through our model checker. uh, so model checker is running for correct normal model config. I have added the logs as well, print statements, so that we can see what is going on right now. And in that case, let's explore what our next statement is doing. Next has 7 action statements. 4 skip slot max is the action which will skip the maximum slot, because we have to end this, right? So we to end this, I have written the logic in the way that it will skip the maximum slot. Okay, leader generate and send the shred. So the leader is chosen, and they can generate shreds from the transaction which they got, and they can send the shreds to a relay. So relay broadcast thread is an action which will broadcast that. So relay nodes will take that shreds, and they will broadcast that shreds to other validators, other nodes. So, and this is the node reconstruction block. This action is to get the shreds from the relay node and to construct the block from it. And block ready is when the block is ready, then we'll do other processes. And process slot is to increment the slot and increment the timer and all. And log consensus status. So consensus, at every checkpoint the log will generate, which will log what is the current state of the consensus. Okay, So in process slot, as you can see, the if the current slot is less than maximum slot, go further, and global time plus 1 is less than equal to maximum time, go further. We can increment the global time. And after that, these all are the asynchronous processes, like event generation, like event triggers, like uh, slow finalization or fast finalization events, or save to notar events, or save to skip event. These are the events which is which happen individually on the each node, and these are the asynchronous tasks. So I have encapsulated all the asynchronous tasks in one action only, which doesn't depend on any network latency or anything such that. So these are only the local nodes asynchronous actions. So yeah. So uh, as you can see, this is the log consensus state. This logs the current slot, global time, finalized blocks, how many blocks are finalized, and skip slots. Some slots are skipped as well, and current leader, who is the current leader, and the disseminated block slots, which are the slots which are done processed. Okay. So these are the variables which we had taken to inculcate our TLC model checker. So first variable is a global time, second variable is a current slot. Global time shows that what is the current time. So because every action we increment the global time. And current slot, what is the current slot, because this will help us to know the real world significance. And node state. So node state is a set of state flags, node and slot. And block state is block store of node of slot, set of blocks received by a router. And pool events and the certificates are stored in pool. Votes are stored in votes. So these can be accessed, like votes of node of slot, and vote type of block id. That means what is the current vote count for a node in a particular slot of vote type, because there are different vote types. So skip vote, or notar vote, or for skip fallback vote, whatever votes are there, that can be this vote type. And block id. So yeah. So block id is a block which we are processing. And vote count, what is the vote count. So yeah. So timeouts, also we have added a timeouts logic as well, and a pending blocks. What are the pending blocks which are used, which can be used for a retry. And events, set of events, like save to notar, save to escape. And notar messages, message in transit, what are the messages in transit. Byzantine actions, track Byzantine equivocations. So this help us to check whether a Byzantine node is doing two getting to go two votes or not. Okay. And that's it. Finalized blocks are kept in that, so that we in next time when leader is processing a block, then the block should be a different. And skipped slots, some slots are skipped as well. So we had added a timeout logic as well, skip slots as well when timeout is triggered. And these are the disseminated slots and disseminated blocks, so to track which slots are processed and which blocks are processed. So these help us in checking the current state of the consensus, which I had logged in. So yeah. Okay, so let's go into the proof part. If this consensus get runs, so we have like save to skip event and save to notar event as well. So save to notar event triggers when window skipping, and noter fallback voting. So this save to skip event is triggers when skip fallback voting. So for this we have all the checks like current slot is less than max slot, has voted, because this has to be a voted previously as well, right? This should not be a noter voted, this should be a skip voted. So as you can see, we have checked the vote of n for this node, and for this slot skip of so we skip, for a skip we have a block id of none, because in skip we don't have any block, right? So for consistency we have chosen to make it none. So we can check that this has a skip vote, but this doesn't has a noter vote. So save to noter not in the events, and yeah. So save to noter is not in the event. Okay, we will add that into the event next, right? So this is the event trigger. So okay, so as we can see, the b let statement b is equal to choose, so choose any block in the block store. So check if it is so save to noter condition or not. Save to noter condition is the you can see like noter stake is vote stake, s of notarization of b, skip state or skip state s. So noter stake, you can see what is the code for the noter stake as well. Noter stake is cardinality of nodes such that for which they have greater than 0 vote for this block. So vote stake, so vote stake is the node stake, and the skip state we can say that what are the nodes which had skip, or is the skip fallback vote for this particular node. So we can calculate that, and after that we can see if the noter stake is greater than equal to save to noter threshold, then this can be considered to as a save to noter condition. And if the skip state plus the noter state is greater than equal to a slow threshold, or and noter stake is greater than equal to fallback threshold. So we have these thresholds as well as defined in the research paper. Like the fast threshold is 4 times of total stake upon divided by 5, 4n by 5. It is 80% for the fast finalization. Slow threshold is 60% for the fast finalization. Byzantine threshold is 20% Byzantine threshold, and fallback threshold is 20% minimum for the fallback, right? So yeah. So yeah, we can, so this will run according to the code, and according to the we just have re-implemented the logic which we had for algorithm 2, algorithm 1, and algorithm 2, and algorithm 3. So that this can check whether the things which are in the research paper that are consistent or not. For that we have added the invariants like safety, theorem 1 safety, certificate uniqueness, non-equivocation, so that the no node can vote for two blocks at the same time for a single slot. So chain consistency and Byzantine resiliency property, no malicious finalization, Byzantine resiliency, no double voting. Yeah. So okay, so as you can see, this has completed. This was the normal model checking, correct normal model config. It took around 13 minutes and 29 seconds to complete this, and as you can see, it has explored around how many states? 8,44,423 distinct states. And you can see the current state as like first slot was a genesis, second was proposed by a block 1, and third slot was proposed by a block 2. And as you can see, we can go through this log file which stores all our logs. And yeah, you can see like there are almost these number of states which has third block process, because we had a maximum of 4, right? we had written a maximum slot to a 4. So according to that, we will have second slot and third slots to be processed, and first is a genesis. So yeah, so you can see some state will be like only uh, 3 is processed. Yeah, let me show you those as well. uh, okay, as you can see, the current slot is 4, global time is 5, finalization blocks are this, skip slot nothing, no blocks, no slots were skipped, and the current leader is n4, and disseminated slot is this. uh, so yeah, we can go through this. So if timeout would have occurred, they would have skipped as well. But as we can explore all the states, we are not able to see any slots among 2 or 3 getting skipped. So yeah, so this might be a case like they would have not skipped, so that's okay. So yeah, let's go to let's run now the Byzantine node as well. So for Byzantine we have this. So yeah, let Byzantine one running. So for Byzantine one, like we have choose a node, we have increased the node size to by one, so that we can have 5 nodes, and out of that 20% threshold. So 20% of 5 is 1. So we have one Byzantine node, and we have malicious blocks as well, which will be proposed by a Byzantine node. And yeah, I can show you the logic where um, Byzantine node propose the block. uh, so yeah, you can see this. Yeah, Byzantine leader should encode different blocks. So yeah, these are the Byzantine leaders, and encoding shreds for the block, current block, and malicious block. So these can propose two blocks, and the current block only propose the correct block. They don't have a malicious shred blocks. So yeah, as you can see, this will complete. This will around take 55 minutes, because that one of the correct version would have that taken 13 minutes. This will take around 50ish. So yeah, so let's go into the proof part. So we have a machine verified proofs as well. So yeah, let's go into the proof part. So yeah, before we look at actual proof, let me explain TLA plus proof syntax. Like so theorem statement declare what we are trying to prove, and the proof block, this is the proof block. So this proof block contain the actual proof. They are hierarchical using numbered level like 1 2, and which are encapsulated by the arrow brackets, and each level has have sub levels. The number help us track where we are in proof structure. So suffices, some places I have suffices is a powerful technique. It says to prove the goal, it's sufficient to prove this simple thing. You use it to transform the proof obligation into something more manageable. So yeah, so we can assume that we have to prove this, and assume this, these are the true, and we have to prove this. So yeah, so there are by clause as well, which indicate that a step follow from a previous step or definition. Like by 1 2 means this has been followed up by the 1 2, and definition is to take into the place the expansion of the definition for votes take into this place. So yeah, proof omitted in is our way of saying like we know what the proof should look like, but we cannot complete it in a TLA plus TLA PS yet. We will see why that happens. And quad marks the end of the proof. So yeah, these are the quad which marks the end of the particular subproof. So yeah, let's start with our first complete proof, invariant hold in it. So let's start with something we actually provide completely. So yeah, so for all nodes and slots, so for all nodes and slots, uh, if a node hasn't voted, then all its vote counter must be zero. Like so, if it is a init state, so initially all the votes will be zero. This seem obvious, but it's a foundation. Let's prove it. So it's just an example proof. So I have written this to learn like how we can prove things. And proof begins as suffices assume that init is happening, and init is we are in init state. And prove we have to invariant known vote implies zero. Okay, so claim that so 1 2 claim that in the initial state no node has voted, flag set. Why is it true? Look at the by clause. It says by step 1.1, which assume init, and using the definition of init node state, uh, all votes are zero. Like 1 3, you can see like all votes are zero. uh, uh, 1 3 claims all votes start at 0 again by step 1.1 and definition of init. Let's verify line 1. uh, so in line 142, as you can see, yeah, so we have initialized everything by vote 0. So that means we have proved our statement like vote will be 0. So yeah, where is that proof? Yeah, so all votes are 0. uh, that means this proof has ended. So the final step, we have shown no node has voted and all vote counts are 0 as well. By the definition of the invariant, no vote implies 0. If voted is not in the node state, then no votes must be 0. Right? We have proven both parts, so the implication holds. Okay, so yeah, so let's go into our another proof or lemma. So lemma 20 says that each correct node cast exactly one notarization or skip vote per slot. So they can either cast a notarization vote or a skip vote. So let's start to prove this. So we assume that let's parse this. We assume that new n and s, we are proving this for an arbitrary node and slot. Like for arbitrary node n in nodes and s in slots, and we have type okay, and invariant no vote implies 0. So type okay, this system is well typed, and invariant no vote implies 0, our proven invariant hold. So this proven invariant hold as well. And this is not a Byzantine node. So this is not a Byzantine node. That then only we can say that they they both will not they both will not vote for the node will not vote for both vote types, notarization and skip as well. So what we have to prove, a notarization is not equal to block 0, and skip none is equal to 0. So if there is a notarization vote, there will not be a skip vote, and if there is a skip vote, there will not be a notarization vote. So yeah, So prove a disjunction or we have to prove this or statement. So take a case when voted is not in node state, so it has not voted yet. So if it has not voted yet, invariant say if no voted in invariant no vote implies 0 says if voted is not in the state then votes are 0, therefore votes of vote of ns and notarization, vote of nsv any type and block will be 0 for all vote types and block as well, right? So what we have checked here as well, for all vote type in vote types and block id, vote will be 0 by the definition of no invariant no vote implies 0. And so this is the clause. And so step 3.2 step 3.2 specializes to notarization from step 3.1. We know votes are 0 for all vote type, notarization is one of the vote type, so notarization vote are 0. So tla ps verifies this. Function extensionality problem is the reason due to which we have proof omitted here. So what happened here was that where we hit our first problem, we have proven that all blocks b no votes and s notarization b is 0. We want to conclude that node and s votarization equal the function votarization equals this function. But in math this is function extensionality. If two function agree on all inputs they are equal, but tlaps doesn't automatically apply function extensionality. We would need to explicitly invoke a lemma about a function equality, so we mark it omitted and explain why it is omitted. uh, so let's take that also see that if notarization is also 0 then skip is also 0, so skip is also 0. And we claim that skip is also 0. And after that we see that if function equals 0, skip is also 0, then this is one tlaps can handle because we are just extracting a specific value. Okay, so as you can see 2.3 state now. So 2.3 state, if the function equals the 0 function then all its values are 0. This is obvious and it is so this was obvious and proof emitted. So again this was the case when no vote was there. If node has voted, so if node has voted and so this case 2 is more complex. If node has voted, we need to show it voted for exactly one thing. This requires reasoning about how the voted flag gets set. So voted flag gets set by these two actions, try noter vote and try skip vote. So as you can see, let's try skip vote. Yeah, so try noter vote and try skip vote are the thing that sets voted. So these also has a voted statement. So for this, as you can see, they are mutually exclusive. They can't execute both, because for this we check if they are not has voted. So has voted check for this only, they if they have voted in their node state or not. If they have voted, then they can only try noter vote only, then that cannot happen for run for a try skip window. So yeah, they are mutually exclusive. So that's why they can either vote for a noter or a escape vote. So yeah, so by this I have proved a lemma 20 holds, and let's go to lemma 24. Okay, so for lemma 24, let's tackle a certificate uniqueness. At most, one block can be notarized per slot. This is absolutely critical for the safety. So, as you can see, we assume that type OK is there, Byzantine resiliency is there. That means Byzantine nodes are less than equal to 20%, and cardinality of Byzantine nodes are less than the fallback threshold, strictly less than 20%. We prove the certificate uniqueness. Here we prove the certificate. By the way, certificate uniqueness is also proved by the model checker, but the model checker is running for a small number of nodes. Then for the expanding extensionality of our theorem, we will prove this here as well. So yeah, certificate uniqueness means what? That for a particular, for all slots, for all s in slots, cardinality of has notarization certificate for a block in particular slot is less than equal to 1, because in a slot there cannot be a two blocks with a notarized certificate. So that's the certificate uniqueness. So for that, setting up the proof, we in 1.1 we transform the goal. Instead of proving the cardinality statement directly, we prove the contrapositive. If b1 is notarized and b1 and b2 both are notarized, b1 does not equal to b2, then b2 is not notarized. That means if we have any slot in slots and b1 in block id and b2 also in block id, and b1 b2 both are not equal, then has notarized certificate for this slot and this block 1 is, if this is valid, then this will not be notarized, because there can be a one block with notarized certificate in a particular slot. That we have to prove. Okay, so for that we we go into the cases like suppose if b1 has 60% of vote, if notarization certificate with slow threshold, if b1 has 60%, if b1 has 60% vote, and step 1.2 unwrap the definition, has notarization certificate is defined, and setting, so b1 has, if b1 has a 60% vote, has notarization certificate by the definition. So let define a v1, the set of nodes that voted for b1. It claims that v1 greater than equal to slow threshold. So these claim that v1 is greater than equal to slow threshold. uh, s- uh, so so why we are saying the votes take literally count node that voted. So 1.2, as 1.2 states that notarization vote count for a slow threshold, therefore v1 greater than equal to slow threshold. So so step 1.4 comes. In 1.4, we have v1 and v1 underscore correct. So v1 is a total nodes which has voted for notarization for a v1 block. v1 correct is v1 minus Byzantine node. If they have as any Byzantine node, we will exclude that. So Byzantine node is less than fallback threshold. So v1 correct is v1 minus Byzantine node. We want to show that v1 correct is greater than safe to noter threshold, that is 40% of the node, and the arithmetic v1 correct greater than equal to So this is v1 minus Byzantine node. v1 is greater than equal to v1 minus Byzantine, greater than equal to slow threshold minus fallback threshold, greater than safe to noter threshold. So safe to noter threshold is 40%, slow threshold is 60%, and fallback threshold is 20%. So this can be easily proved, so that's why we have omitted here. And as you can go further, uh, so as you can go further, 1.5 is crucial. It says that correct node in v1 doesn't vote for v2. So as we know that correct node cannot vote for double time. If we have chosen it to be a notarization, that cannot vote for v2, right? So n in v1 correct means n not in Byzantine node, so is not in Byzantine node. And votes count for n to be notarizing the v2 is 0, because they have already voted for v1. So with this condition, the second part requires the lemma 20 notarization or escape. If node n voted for b1, it cannot vote for b2. b2 does not equal to b1, but lemma 20 was complete. Okay, so b2 cannot reach threshold, so that's the correct part. Okay, so after that we can see 1.6 as well. We assume that node votarization count greater than 0. v2 is that nodes which have votarization count greater than 0, the cardinality of v2 will be less than slow threshold. So v1 correct is greater than safe to noter threshold from 1.4, and all nodes with weaver current do not vote for v2 from 1.5, and v2 is less than total stake minus safe to noter threshold. So that will be less than slow threshold, because safe to noter threshold is 40%. So if safe to noter threshold was greater than v1 correct was greater than safe to noter threshold, that means 40 greater than 40% vote were in v1 correct, then how can we get a greater than 60% vote for v2? We cannot get this greater than 60% vote for v2. We will get less than 60% vote for v2, right? So they cannot be notarized. Notarization vote will be less than slow threshold, so they will not be notarized. So we have proved lemma 24 as well. So in theorem 1 safety proof, this is the main proof. For this we assume that type okay, well type system and Byzantine resiliency is there, no double voting is there. So we have assumed these things, and no double voting is there. Cardinality of Byzantine nodes is less than equal to Byzantine threshold, that is 20%. So we have assumed these things, and we have assumed this like for any arbitrary slot, if there is p1 in block id and b2 in block id, and s of b1 in block finalized block, s in b2 in finalized block, then both b1 and b2 will be same. That we have to prove. So that means the one block will be finalized for a particular slot. That is what we have to prove. So to prove this, we transform statement 1.1, the universal quantification, into specific assumption. We assume b1 b2 are both finalized in slot s. We need to prove they are equal. The by clause indicates this follows for definition of theorem 1 and type okay correctness. So yeah, both are fast finalized. If we assume this both are fast finalized certificates, we split on finalization type. Both block has finalized 80% votes. Both block has finalized 80% vote. So greater than equal to fast finalization, greater than equal to fast finalization, both have finalization vote. We assume this. Okay, let's go. We assume this. After that, v1 is the count for the nodes which had voted notarization. So greater than equal v2 is also that. So cardinality of v1 v2 is greater than equal to fast threshold. v1 is subset of node, v2 is subset of node from definition of vote stake and type. Okay, v1 is also again v1 v2 we have calculated, and v1 cap v2 is greater than slow threshold. So v1 intersection v2 is greater than slow threshold. So for this, if till this point we know that v1 is greater than equal to 80% vote. The count of v2 is greater than equal to 80% vote. By the inclusion exclusion, v1 intersection v2 is greater than equal to v1 plus v2 minus total number of nodes. So v1 intersection v2 is greater than equal to 80% plus 80% minus 100% is equal to 60%. So that means v1 plus v2 is greater than equal to v1 intersection v2 is greater than equal to slow threshold. Actually, we need strict inequality. Since fast finalization 4 times of total stake by 5, we are using integer division. There might be rounding, but intuitively 80% plus 80% minus 100% greater than 80% should hold. So yeah, in v1 and v2 both, there exist one correct node, at least one correct node there should exist between v1 and v2 both. So in cardinality of v1 both minus Byzantine node, that will be greater than 0. This proves that there is some common correct node which had voted for b1 and b2 both, right? So for this uh, for this we go further. In 2.6 we say there exists a correct node that voted for both v1 and v2. This should follow directly from 2.5. If v both minus Byzantine nodes greater than 0, then set is not empty, so there exists an element in it. Okay, we got it. So there is some correct node which has voted for both. So in 2.7, so as you can see, there exists a node in node minus Byzantine node which had voted for both b1 and b2 for notarization certificate. So but as in 2.7 we have a correct node that voted for both b1 b2, but no double voting says correct node doesn't vote for both two different blocks. So two different blocks cannot be voted by a same node. So as you can see, our Byzantine one has correctly been processed. So first let's finish this proof. So as we have gone through 2.7, like we have proved that they cannot vote, so no double voting is there if we had assumed earlier. So no correct node can vote for a different block. So in this case we can see there is notarization certificate. There cannot be a case with notarization certificate for both b1 and b2 as well, because we have proved the certificate uniqueness in lemma 24 as well. So with these things we actually proved that no two blocks can be finalized in same slot. So yeah. Okay, so yeah, so as our model checker has completed, as you can see, 2 3 are processed, because in Byzantine we have also checked took the 4 max nodes. So 2 3 are processed. So let's let's explore some blogs to check whether they have the Byzantine node was able to encode the malicious blocks or not. So we will check this in our Byzantine verifying logs. So yeah, so this has completed. This took around 26 minutes and this has gone through almost 7 lakh states. So yeah, this as you can see, 2 and 3 are processed. 2 and 3 slots are processed as much as I can see. So yeah, so as you can see, they might, some have gone through a fast finalization, some has gone through a slow finalization. Let's see, is there anyone who has gone through slow fast finalization? Yeah, as you can see, fast finalized block p1 in slot 2. Is there anyone with slow finalization? There might be case that there wouldn't be any slow finalization, but if we would be lucky, then yeah, as you can see, these are the slow finalization block b1 in slot 2. These are those events for slow finalization, as rotor reconstruction for node n5 and reconstructing the block b1 is constructed. So as you can see, these are all logs which help us to know whether things are happening according to the code has been written or not. So this will help someone who is exploring this code. So yeah, so let's go into the further proofs. Next proof we will be of lemma 33. So in lemma 33, as you can see, this says if a current node has a parent ready for slot S, the first slot in the window, then it has timeout set for all slots in that window. So yeah, this so there is a part of code in 236 which I will 436 which I will show you, where we set timeouts. So yeah, this, so parent ready, if current slot is less than max slot, is the first slot in the window. Yeah, this is the first slot in the window. Has parent ready already happened previously as well? No, not happened previously as well. So parent is ready right now. And the pools, so pool store the whether parent is ready or not and that kind of states. So as you can see, we have a window slot and we new timeouts, we set the timeouts as well. So timeouts is set as a new timeout for this particular node. So new timeouts is set for the coming slots for this particular node. This is the formula which was there in the white paper. Global time, current global time plus the network delay plus s2 minus current slot plus 1, the index of the slot in this window into block time. What is the block time which we have taken in the model config. So this action tell us that we already have set timeouts as well. So yeah, so let's go into proof. Yeah, so as you can see, we have a parent action in which set the timeouts. So yeah, we have timeouts set for the window. So yeah, so let's move into the lemma 35. Timeout implies vote. So what this says is, if all correct node has timeout set and process timeout is fair, then all correct node eventually vote. So eventually eventually they eventually vote, uh, because we have process timeout in at the top. And if the node hasn't voted by the timeout, it calls the try skip window, which sets the voted flag. So either they will vote, or if timeout would trigger, then they will try skip window. So you can see this in process timeout. uh, in process timeout you can see, yeah, either they hasn't voted yet, then they will try skip window, or if this timeout is not triggered, then they will obviously vote. So yeah, that is voting guarantees there. Yeah, so lemma 35 is also proved. So as you can go further, we go for lemma 36. So in lemma 36 as well, we say if no block has greater than 40% votes, then no correct node enter its over state. Yeah, so to prove this, we have assumed that if n is a correct node and it's over in the node state, then prove this is false. uh, so to so we will prove this by contradiction. Assume some correct node has its over and derive this is false. So to derive the contradiction, we need its over is only set in block notarization action. Block notarization requires has notarization certificate. Has notarization certificate requires vote state greater than equal to slow threshold, but assumption say all block has vote state less than equal to safe to notar threshold. So 60% is greater than 40%. Why this contradiction? Logic is all right. That means we is vote over will never happen, because we have assumed that for this lot, for all blocks in block id, notarization vote count is less than equal to safe to notar threshold. That means this will never its over state. So yeah, we have already proved that. So let's go to lemma 37, where we say that this is a key liveness lemma. Either skip certificate forms or some block get greater than 40% vote. So by lemma 35, all correct nodes vote. Correct nodes are greater than equal to 80% of the stake. So we have 80% vote distributed among notarization vote for various blocks and skip vote. Let's say block vi get vote share vi, then summation of vi plus skip votes is greater than equal to 80%. Two cases now. Some vi greater than 40%, done. Second clause hold, and second clause holds, and all vi less than 40%, then skip vote must be greater than equal to 80%. Total notarization, if no single block exceed 40%, we have multiple blocks eventually skip votes greater than equal to 60%, has a skip certificate holds. The argument is rigorous. So yeah, so we go into proving the lemma 38. So in lemma 38 says if greater than 40% vote for b and action are fair, greater than 40% safe to notar vote for vote b in this slot, an action is fair, then eventually a notar fallback certificate forms. So let go to a temporal chain. So vote stake, if that is greater than 40%, safe to notar condition become true, and safe to notar event trigger for all correct nodes. Correct nodes cast notar fallback vote. Eventually, vote stake plus vote stake for notar fallback and vote stake for notarization is greater than equal to 60%. Has notar fallback certificate votes. So yeah, so we have proved that if greater than 40% vote for B and action are fair, they eventually a notar fallback certificate forms. Okay, so let's go to theorem 2. So to prove theorem 2, what is theorem 2? So this tackle main liveness proof. So what we have to prove is there exists a block in block id such that s comma block in finalization blocks, or s in skip slot. Either s will be finalized with some block or s will be in skip slot. So the assumptions are, we have type okay, we have Byzantine resiliency, that Byzantine node is less than 20%. New, we take any slot, and the post GST global time is sufficiently advanced with the network delay plus block time, and we are in asynchrony, and so 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 this will already happens, because if lemma 41 all correct node eventually set timeout, lemma 42 the parent ready propagates within the network delay, rotor latency block arrives within 2 times of network delay, and timing block arrives before timeout fires. So lemma 35 all correct node vote. Byzantine resiliency is greater than equal to 80%, so correct stake vote for the same block. So fast threshold reach. So yeah, so let's uh, so what is the next proof left? mm, so yeah, let's run all the proofs now. So yeah, we will run all the proofs. So this will run all the proofs. So as you can see, all 53 obligations proved. So yeah, that was my time.